Hey everyone, this is Sandip back with another video. And in this video, I'm going to talk about big O expressions. Yes. So in the last video, I think this is more of a continuation of last video. So in the last video, we were checking the performance of two different programs, right? So there was one program which I have written using the for loop, and there was another one which we have written using the formula. And you might have checked this formula on the Google, maybe. And we have seen, like in the first program, as the input grows, the performance of the program goes down. And I mean, it takes a lot of time to add all of these numbers together. And in the second program, where we have used the formula, right, as the input grows, the time remains the same. So I'm not going to run this program again because if you want to see that, I mean, if you want to see the performance of these two programs, I'll put a link of the first video in the description and you can go and watch that. So we were discussing, right? I mean, using the formula and this performance now formula, which is more of a time based, is not a good idea, right? Because it depends on the machine time. It depends on the machine of the user, right? So we can't rely on this performance.now, but it gives us a guesstimate, right? And we can, I'm not completely denying that you cannot use this way, using the performance.now to identify the big O or a performance of a particular algorithm. You can definitely use this particular strategy, but to have a right thing, I have created some slides and let's jump into it. So big O expressions, right? So let's talk about the second program. So maybe if we don't rely on a time, let's talk about the number of operations which are happening inside a particular algorithm or inside a particular function. Because these operations, because of this operation, the number of operations which are happening, it gives us some indicators towards the performance of a particular program, because calculations are more of a CPU dependent, right? So the CPU actually does all of this calculations. So let's take the second way of add up to n, where we have used a formula. How many operations are happening here, right? So we are having one multiplication, one addition, and one division, right? So when the value of n is 1, we are going to have one multiplication, one addition, one division, right? If the value of n is 10, again we are going to have one multiplication, one addition, one division. If the value of n is 1 million, right, you're going to have one multiplication, one addition, one division. So as the n grows, right, our multiplication, addition, and divisions are not growing, right? That's the reason, I mean, this program is performing at a constant time. It's giving us the output in a constant time. And if we come back to our first one, right, where we have used for loop, right? So first time we are creating this as sum variable, right? So this is assignment. So I'm going to say one assignment. Here we are running a loop, right? For loop, where we are going to assign once only, I equals to 0. So this is one assignment. And then we are doing the comparison of I with n. So this is n comparison. Why n comparison? Because if n is 1, I'm going to do comparison once. But if n is 10, I'm going to do comparison 10 times. If n is 1 million, I'm going to do comparison 1 million times. Similarly, we are doing I plus plus. So this is n additions, right? Because 1 n, 1 addition, 10 and 10 addition, 1 million and 1 million addition. And now we are moving into the loop, and here there are two operations. If you look at it carefully, there are two different operations which are happening here. So we are going to have an addition and an assignment. So if I calculate, if I do addition of all of these things, it is going to come somewhere 1, 2, 3, 4, 4n plus 2, something like that, 4n plus 2. So why I'm talking about this 4n plus 2 and everything, right? Because we need to give some value to our algorithm, some big O expression, right? Okay, we should be able to identify what is the big O of this particular function or this particular program. That's where we are heading towards, right? So that's where, we are going to talk about big O expression. So big O helps us identify the runtime of an algorithm. As input grows, the runtime of an algorithm grows too. And we have seen that, right? In this example, as n grows, our performance goes down because our runtime grows. But in case of first example, it's the constant time, right? That's where we have three different big O's. There are many. I'm going to talk about first three because these are simple to understand. And then I'm going to jump into other big O's, in the upcoming videos, not in this video. So given an algorithm, right, given a function, we need to identify whether its big O is O of 1. O of 1 means constant time. So as n grows, the runtime of a program doesn't grow. It remains constant. That's where when we say that particular algorithm has a big O of 1. I mean, it's a constant time. And we have seen that example, right? Our first one, this formula, right? Here the big O is O of 1 because as n grows, our runtime of program doesn't grow. It remains constant. That's why we can call this algorithm, this function, we can name it O of 1. Next is a linear time, right? Fn O of n. So as the input grows, in case of linear time, as the input grows, our runtime of our program also grows. So if n is 1 lakh, it's going to take some more time to execute that particular function. So that's where we call it a linear time, and we have a good example of that. The first example which we have created, add up to n using add up to number using for loop. So in this case, as the value of n grows, our runtime, our performance goes down because our runtime is increasing, right? So this program, we can call it has a big O of n. And then there is a third category which is called quadratic time, where which is horrible. I mean, which has O of n as n square. So as n grows, your performance degrades, exponentially, I would say. And we can, so I'm going to give you an example of quadratic times. I have written one program, O of n square. So whenever you see a for loop multiple times, so I have this print all pairs where, I'm running two loops. For first for loop up to n, and second for loop which starts with j up to n. So if you want to print 100 pairs, right, this is how it is going to print. Let's try with a simple 5 as an input value. Now I'm going to run it. So I'm going to first clear this and run it. So this is how it's going to print the pair 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 1, 0, 1, 1, 1, 2. So it's going to run all the pairs of this number n. So as the value of n grows, its time is going to increase exponentially because the n is running for 2 times, I would say. I mean, n into n, that is 5 into 5, 25 times here. So in case of 1000, it would be more, 1000 to 1000, something like that. 1 lakh into 1 lakh, 1 million into 1 million. So whenever you see those two different loops, that is more of a quadratic time. So the big O of that particular program is going to be O of n square. So we can chart it, right? So this chart you're going to see everywhere we talk about big O. So this line, x-axis designate the input, and this y-axis is a time, right? So as the input grows, and if my time is not growing, not increasing, right? So that has a O of 1. This is green, right? So this means if your algorithm, if your program has a big O of 1, that means it's a fantastic program, right? Because as the input grows, your time is not increasing or growing significantly. I'm not going to talk about O log n. Let's talk about O of n. So as the input grows, your time grows, right? So that's why this line is like 45 degree, linear. That's why we call it, linear time. And finally, we talked about O of n square. So I'm going to talk about log n later on. O of n square, where you see those two loops, right? So where as the input grows, I mean, your time is like taking a lot of time. Even for a small input, right? It's taking a lot of time. So that's called, the quadratic time. So whenever you're going to write any function, any algorithm, right, we're going to categorize them. We're going to give them big O expression, the big O of 1, big O of n, or big O of n square. So constant time, linear time, and quadratic time. There are some other times which I haven't talked in this video, but we will cover that in the upcoming videos. So quickly, right? We talked about different counting operations, right? We can count the operation if we are not Relying on the time, we can count the operation, and based on the operation, we can calculate we can guesstimate the big O of particular uh, algorithm, right? And we have categorized our algorithms, expressions into three different categories in this video at least: constant time, linear time, and quadratic time. So big O, it helps us identify the runtime of an algorithm. As input grows, the runtime of an algorithm grows too. So I think that's it for this video. I just wanted to quickly talk about different big O expressions, which we're going to which are going to come when we are going to write a lot of programs, when we are going to talk about different data structures and algorithms around it. So there, the big O is going to come. These expressions are going to come. That's why, I wanted to cover these topics first before we move on and talk about the actual data structures and algorithms. So that's it. I'm going to stop here. I'm going to see you in the next video. Until then, you take care and goodbye.